right, if you guys have not done so already, please get a picture of your homework. Make sure you have that to track along with. And then turn it in up front here, because we'll be going through the homeworks 1 and 2 together. Want to make sure that we have your homeworks, but you can also look at your work. So hopefully it's a bit more useful for you that way. So when are you getting home? When will you be home? Okay. Can you just scan it and email it to me as a PDF?
Yeah.
Okay.
I didn't get to print the Excel sheet for number 4, so I turned it in after one. That's okay. Do you have a statement?
I don't. Sorry. Is your name on each page?
Yeah.
Okay. All right. So I want to get started, but I've got a couple quick announcements first. So you know the exam's Thursday. I do apologize. I know a lot of you have a couple other exams that day. As I said in my email, I'm sympathetic, but I learned of that a little too late, in part because next week I'm going to be out of town, and so I can't give a test next week for you. So the plan for next week, I'll have a guest lecture. One of my graduate students will tell you about some fancy water treatment processes that we're doing research on. That'll be advanced oxidation processes. Something, maybe I'll have a small quiz for you at a later date. That lecture will not be recorded and will not be broadcast live. So I apologize about that, but my grad student is not set up the way I am, and I'm not going to try to get him to learn all that for Tuesday next week. Thursday next week, so a week after our exam, I will be delivering a lecture from remotely, basically staying with some people. I'm going to just be in their living room or something, and I'll give the lecture through the Twitch platform. So don't come to class a week from Thursday. Obviously come to class for the exam. But that following Thursday, and I'll email you to remind you, class will just be remote that day. Okay? So it'll be a guest lecture and then a remote lecture, and then we'll be back to person like normal after that. So, I think there was one other thing I had to say regarding that. Oh yes, our makeup day is supposed to be this Saturday. My plan is to, instead of have just an in-person makeup day, I'm going to do that remotely, and what it will be is I'll go over Thursday's exam. I'll go over the solutions with it. So you're welcome to tune in live to kind of work through any issues you had. Hopefully I'll be able to grade your exam and get them back to you once I'm back from traveling, but obviously you will have just turned in your exam. So I may host that on Friday because I start my travel on Saturday. So I'll let you know. I think it'll be Friday in the mid-afternoon. If you guys have concerns about that, you really want to make sure you're there or something for it live, you can let me know. Happy to work with you, to do a separate time if we have to, or to figure that out. But that's my plan for the makeup. That's my plan for next week, which I'm out of town, and for the exam. So any questions about those logistics? Okay, so I'll start going through the homework. So again, if you came in late, make sure you've submitted it up here, take a picture of it, so you'll have it as a reference. So I'll go ahead and get going with this. I'll make sure we have a little time at the end for questions about the exam itself. And if I don't get to both sets of homeworks, then what I'll do is I will finish writing the solutions after class. I'll make sure to post that tonight so that you'll have the full solutions to study from tonight at the latest, and you'll should be all set to go. So that's the plan. We'll see if we can get it done together though. Okay, so homework 1, problem 1, we had a dry cleaning company. It's buying a barrel of dry cleaning fluid every month. 90% of the fluid is lost to the atmosphere, 10% remains as residue to be disposed of. We have a density. We're asked to draw a mass balance diagram and then estimate the monthly emission rate to the atmosphere in kilograms per month. So we need some rate, kilograms per month, where we have, let's just imagine that we have our little dry cleaners. We have barrels of this dry cleaning fluid coming in, and we have some emission, evaporation leaving, and we have some waste that's disposed of as liquid form. So we know the first thing we ought to do is draw something, right? Draw your system, draw the diagram. So this is how I'm drawing it. We have 2 exits, 2 ways that the stuff can leave, the evaporation and the disposed as waste. And what we want to know here is estimate the mass emissions to the atmosphere. So the rate at which mass is leaving to the atmosphere in kilograms per month is what we're looking for. Okay, and that might be helpful too when you first start working on a problem. Write down even the units that you're looking for or that you expect you're looking for. Right? In this case, it was given here. Okay, so that's what we need to solve for. We are given that it's 1 barrel per month, and that is 0.16 cubic meters per month. That would be a flow rate going in, and then we can use that flow rate plus the density that we were given to get some sort of mass per time. So remember, pretty much all of our mass balances are going to come down to mass per time units. So whether that's a concentration times a flow rate, or maybe a flow rate times a density to get us to a mass per time unit, either way it should work. So our density here is 1.5940 grams per milliliter. We have this barrel in cubic meters, and we later want kilograms. So I'm going to go ahead and say up front, let's convert this into kilograms per cubic meter. So we can multiply this by, let's see, 1 kilogram per 1,000 grams. That'll get us to kilograms. We also want to multiply by 1,000 milliliters per liter, and by essentially 1,000 liters per cubic meter. Okay, so that's basically on the net, that's multiplying by 1,000. So we can say that our density here is 1,594 kilograms per cubic meter. Okay, so that should simplify things, help us out there. Now we have everything in the same units. So for our mass balance, what we want to know is how much is leaving for evaporation. Well, this is a steady state system. There's no reactions or anything going on, so we can say what's coming in is equal to what's going out. We can get there if you wanted to from our accumulation is equal to 0, which is equal to what's coming in minus out plus the reaction terms, which is 0. So either way you go, it comes to in equals out. So what's coming in is essentially this 0.16 cubic meters per month. And if we multiply that by our density, that's going to get us from cubic meters to kilograms, right? So we've got this 1594 kilograms per cubic meter, multiply it by this. That should give us our mass on the left, and then that's going to be equal to the outputs, which we know we have some waste.
Isn't it 1.594, not 1594? Like down there, you have like 1,000. Did you multiply that by 1,000? Because I thought 1,000 canceled that.
We have 3 1,000s
Okay,
in play.
Okay, that makes sense.
Sorry, okay. Yeah, so it should be 1,594. Okay, so for the mass balance for our input, we have whatever this product is, and then for the output, we have the waste plus, and we're given some information about what is lost to the atmosphere, or excuse me, what is lost to the waste. So we have waste, and we know that is essentially 0.1 times what's coming in. And so what's leaving from evaporation, we kind of didn't need the mass balance component, but you can solve it this way, and it's sort of asking us to do this. So let me get my calculation up. Just a moment. All right, so essentially what we can say is this here, this amount coming in is equal to, instead of writing it as just the waste, what we could do is write it as 10% of the in plus the evaporation. So we can say this is equal to 0.016. So I just took this one barrel and said, okay, well, let's take a tenth of that. So it's a tenth of a barrel, cubic meters per month, times, of course, the density. Plus the evaporation. So obviously you didn't have to write all this out. You could have just taken 90% of what's coming in and just solved it that way. But doing it this way, it kind of is a little bit more thorough. So you get a number over here, you subtract from that this product, and that's your evaporation rate. Okay, so it turns out once you do this and solve, you get an evaporation rate that is equal to 229.5 kilograms per month. So that's a lot of solvent. This is one of the issues we had early on in the Industrial Revolution when we were, or industrialization, when we were discharging lots of dry cleaning solvents, which were chlorinated solvents typically, into the atmosphere, a lot of them evaporating and then deteriorating our ozone layer. Okay, so any questions or issues with that problem? Okay. So problem 2, we have gasoline vapors, and essentially this problem is talking about 2 different cases when we have gasoline lost when we fill a gasoline tank. If we're not careful, there's a lot of vapor that's created and it escapes through the valve that we're splashing the stuff into. Or we can have this special splash protection where we collect most of the gases that are escaping and we fill it by pouring the gas into a submerged liquid rather than splashing it in on top, all of that to prevent gas escape. So this problem is dealing with that. And so essentially we're asked to first draw a mass balance diagram and then estimate annual loss of gasoline vapor in kilograms per year for that splash method. And then also estimate the fuel that is captured, the value of the fuel that is captured or saved if you go from that splash method to the better method. Okay, so first thing is drawing some sort of diagram. Very simply, I just said, okay, we're adding stuff, but also we have stuff leaving, right? This is when we are doing the refill. And here's, again, that escape. It's the same mass balance both ways, except we have a different output rate here for the escape under some conditions. You could also consider that, okay, we're also selling gas. And kind of draw out a full mass balance that way. What we're given is we know that we have some input here for cubic meters per week, I think. Yep, per week of gasoline. And again, we have a density, so we can get that in mass per time units. Our density of gas, that was, I think, 0.8 grams per milliliter. We can use that same conversion we did a moment ago and just say, okay, well, this 0.8 times 1,000 is 800 kilograms per meters cubed. So that's our density there. What we're looking for first is how much is escaping during the splash fill. I'll leave a blank here, we'll fill that in. And this is gonna be in, I think, kilograms per year. Okay, so as we're approaching this problem, getting the units in place, one thing to note here is we've got years that we're targeting, and we've got an input in weeks. So I would recommend going ahead and straight off the bat, let's convert that from weeks to years. So let's say that refill rate, or the input, that was 4.00 cubic meters per week. We can say, to convert to a year, it's roughly 52 weeks, but it'd probably be better to be more exact and use 365 days in a year. So we'll say this will be times 7. It's 1 week per 7 days. We're canceling the week term. And also multiplied by 1 year, or excuse me, $365 days per 1 year. That way, we get years on the bottom, and we cancel the weeks, we cancel the days, and we're good. So that input then should become, let's see, do I have that written? I don't think that I have that written, so hang on. We'll calculate that real quick. So 4 times 365 divided by 7. It's 208.6 kilograms, or excuse me, cubic meters per year. Okay, so when we want to calculate that escape, we really just need to take that value and multiply it by our density here. Let's see. So I should just follow the solutions I prepared earlier today. So just take a moment, make sure I'm okay. So that's the amount, that's the amount that we're adding in. And then in order to calculate the amount escaped, of course, we need this value here, which is what I was blanking on. So to find that amount escaped, we have some fraction of that that's added. Each time we add it, some part of that, this 2.75 kilograms per cubic meter, escapes, right? So that's the escape term. So we're going to start there and say, well, for every cubic meter, we have 2.75 kilograms that escape, and we can multiply this by that number we just calculated, the amount that we're adding every year. And that will give us a kilograms per year of the escaped, right? So that should be here. If we do that, that should be 573.6 kilograms per year. So that would be the first part of the answer. So we'll say like that. Okay, so now the second part then asks us to estimate how much value we save with the escaping, if we capture what's escaping. And the best way to do that would be essentially to calculate how much escapes in the controlled situation where we're controlling how much vapor can escape, and then subtract, okay, we lost this much under the normal conditions, and then we're losing a lot less now. What's that difference? And we get that difference and calculate the value from that. Okay, so I'm just going to then repeat that and say, okay, what amount escapes for, I'll say the controlled fill. And that's going to be, instead of 2.75, we're going to use that 0.095 kilograms per cubic meter. We're still filling the gas station the same amount, so we can use that 208 kilograms per year, or cubic meters per year, rather. So 208.6 cubic meters per year. And so the amount that's escaping in that second case is going to just be 19.8 kilograms each year. Okay, so then if we subtract that from the initial, we can get our saved amount, 573.6 minus 19.8. That'll give us 553.8 kilograms per year saved. And then we need to calculate the value of that. And so here's where we would convert back to our price using our density, because we know that the price here is essentially 80 cents per liter. So we need this in liters instead of kilograms. So we can say, let's multiply that to understand what value we're saving. And I'm going to say value per year. It didn't specify, but I think that makes the most sense. If you decided to do value per week or something, I certainly understand. I could accept that since it didn't specify. So this 553, we take this and we can multiply by, well, we know this density term is 800 kilograms per cubic meter. So that'll be 800 kilograms per cubic meter. And then we need to multiply that by 1,000 liters, 1 cubic meter divided by 1,000 liters. So that'll get us back to liters, because we're going to need to compare that for the price point. And then multiply this by our 80 cents per liter. Okay, so I'll write it up this way. So let's take a look at those units. We've got kilograms per year. We just multiplied that by kilograms, so that does not make sense. We need to divide that. I apologize. You probably, hopefully caught that. So we're going to divide that by 800 kilograms per cubic meter. That'll change what we do here. So I do apologize. I'm going to just go ahead and rewrite this with enough space to just put it all in one spot. So we'll start here. 553.8 kilograms per year. Need to get rid of those kilograms, so we're going to multiply this by 1 cubic meter per 800 kilograms, right? So that's 800 kilograms per cubic meter. So that should get rid of our kilograms. We'll multiply this by 1,000 liters per cubic meter. Now we've gotten rid of the cubic meters, we've gotten rid of the kilograms, so right now we're in volume per time, so liters per year. Then we need to multiply by our price, which is $0.8 per liter. That'll leave us with dollars per year once we do all that. Okay. So it turns out if we take 1,000 times 0.8, that's 800. That's 800 divided by 800. So it kind of all cancels out, and we end up with $553 per year. So it kind of simplifies a lot. So what I'll say is this just equals 553.8 per year. All right, does that make sense? Okay. Problem 3, we have a water and wastewater treatment process. Process is a filtration device. Excuse me, I read that wrong. Essentially, we're going to use a filtration device to remove water from sludge for water and wastewater treatment. The initial concentration of sludge from a softening reaction is 2%. They give us that's 20,000 milligrams per liter. And the volume of the sludge is 100 cubic meters. After filtration, the sludge solids concentration is 35%. We assume here that the sludge does not change its density during the filtration, and that the liquid removed from the sludge contains no sludge. So none of the sludge itself is escaping as we're doing the filtration. So then we're asked to use a mass balance method to determine the volume of the sludge after filtration. So the first thing I'll do is I'm going to draw a diagram, and this time, let's say we have some liquid that contains a bunch of sludge in it, and we're going to send it through some filter. So I'm going to just draw it like this, where we've got some container, we push water through, and it just concentrates the stuff in there. And so then later, sometime later, it's going to look more like this with that filter, and we've stopped pushing water through it, and so that's just that, right? We changed the volume, but all the solids that are in there, maybe it'll help to draw a little bit here. Let's say we have some solids in there. Now they're all concentrated in here. Okay, so that's sort of the scheme here. We know that in this case, the starting point volume was 100 cubic meters. And then one thing we're trying to do is figure out, okay, how much, what's the volume later? We know the initial concentration, so C initial, that's going to be 20,000 milligrams per liter. And we have some C final over here and some V final. So we'll write it that way. Okay, so that's some sort of a visual to work with here. And it says, okay, use the mass balance method. Well, essentially, what we know is the mass initially is going to be equal to the mass final, right? And so we just need to say, I guess maybe we could do like some flow. I mean, we don't have any information on flow or anything, so I would say that our mass balance has to be particularly simple. We're not dealing with time or anything. It's just mass is going to remain the same, right? So based on that principle, the way to know the mass conveniently would be to say the initial concentration times that initial volume, right? Because concentration is a mass per volume. And so we can set that equal to the C final and V final. So quite straightforward here. We know that we know that the concentration is 20,000 milligrams to begin with, so we could write that in. Just because it's a little easier, I'm going to say that's 20 grams per liter. It's the same deal. So here, I'm just going to say 20 grams per liter times 100 cubic meters is equal to some new concentration. And if 2% is 20, then I'm just going to go ahead and fill this in. We know that means that 35% is going to be 350. So I guess I could be a little more elaborate with that. I'll show you in a moment. So that would be grams per liter. See it? Times the volume that we're looking for. Now, the reason we said 2%, if that equals 20 grams per liter, well then that means that 35%, we'd have to say that's 350 grams per liter, right? Just based on, we were given 2% is equivalent to 20 or 20,000. Should work out that way. Okay, so that's why I put that in there, and then we can solve for the volume in this case. And if you notice, we don't really have to get rid of we don't really have to convert from liters to cubic meters, because the liters will cancel when we divide both sides by one of the concentrations. So if we divide both sides by this 350 grams per liter to solve for our final volume, that leaves us with cubic meters on the left side. The other units cancel. So that turns out to be 5.71 cubic meters. And as a quick little double check here, that is in fact less than what we started with, so that's good. That is reasonable. Any questions, issues? Yeah.
How do you get 350 from 35%?
So that was just because they told us that. So the question was, how do I get 350 from 35%? That was because they told us what 2% meant. And so I used that same reference. And I was like, well, if 2 is 20, then 35 must be 10 times that. So that was just a conversion based on what they gave us, yeah. Okay, so problem number 4 asks us to consider the density of water at 5 degrees Celsius and show that 1 gram per milliliter is the same density as 1,000 kilograms per cubic meter. So kind of the same stuff we've been doing. Just really simply, I wanted you to walk through the process. We take 1 gram per milliliter, which is kind of our starting point. You can multiply that by 1,000 milliliters per liter. We can multiply that by 1 kilogram per 1,000 grams. That's going to give us, those units should cancel, and we should get 1,000 kilograms. I think I skipped a step, hang on. That was supposed to be 1 kilogram. Yeah, no, sorry. we also have to convert from liters to cubic meters, so sorry about that. We need 1,000 liters in every cubic meter. So then our liters are going to cancel after we cancel the milliliters. Then we're going to be left with kilograms instead of grams. So that gives us that 1,000 kilograms per cubic meter. Okay, so I just wanted you to kind of write that out, make sure that you were comfortable doing so. Problem 5 says a sample of air containing 8.58 moles per cubic meter of oxygen and 15.93 moles per cubic meter of nitrogen at standard temperature and pressure. Determine the partial pressures of oxygen and nitrogen in 1 cubic meter of the air. Okay, so the partial pressure, that concept where we have some pressure of O2, some pressure of nitrogen gas, which is N2. The deal here is what we're looking for is what fraction of the air constitutes that stuff. Because we're going to assume it's an ideal gas here. That means that the number of moles correlates directly with the volume. So essentially the amount we have in there is directly proportionate to the volume occupied, and which also directly correlates to the pressure, right? So that's why we'll call it a partial pressure. That gives us essentially the amount in there, right? So we need to know each of these guys. In this 1 cubic meter of air, and we have certain values in terms of moles per cubic meter. What we're going to need to do is use our ideal gas law, PV equals nRT, and essentially calculate how many moles are in 1 cubic meter of air or of gas at STP, and then see what fraction of those total moles that are going to be in there are each of these, the oxygen or the nitrogen. So let's calculate the volume, or we know the volume, sorry. Let's calculate the number for 1 cubic meter. So that's going to be equal to PV divided by RT, where volume is 1 cubic meter. So that's going to be, we know at standard temperature pressure, we're at 1 atmosphere, and we're talking here about 1 cubic meter. Divide that by the R value, making sure that we have the correct units. So R here is 0.082056. That's a value of liters per atmosphere, per Kelvin, per mole. And all of that times the temperature, which we know at standard temperature pressure, that's 0 degrees C, that's 273.15 Kelvin. So the units here, just taking a double check, the kelvins will cancel. The mole here on the bottom is really what is going to come to the top, and that'll be our units for the final answer. The liters in the atmosphere cancel with the atmosphere, but we need to change that cubic meter to liters. So up at the top here, we need to multiply that by 1,000 liters per cubic meter. Okay, so once we do that, we will find that the number of moles at standard temperature pressure in 1 cubic meter of atmosphere should be 44.6 moles. This is very similar to what we did when we said, okay, well, how many moles are in 1 liter? We did that and we said, or excuse me, how many liters does 1 mole of a gas occupy? If you remember, we did that, it was like 22 at standard temperature pressure, or if we did it at 25, then it was like at 25 degrees Celsius, room temperature. then it would be 24 liters, 24 and some change. So this is kind of the same concept. We're just really dealing with how many moles of gas are going to occupy that volume. So once we have that, then it becomes really easy to get our partial pressures here. So we'll say that's moles per cubic meter, because I just solved it for 1 cubic meter, right? That's why I can write it that way, or I can write it just as moles. So when we have these values, we can just take that, we can take those values and say, okay, well, the partial pressure of oxygen is just going to be that 8.583 divided by that total number of moles, and that's going to get us our partial pressure. That's going to be unitless, or we could maybe, I guess, write it as, moles per mole or something. But it's really a fraction. Partial pressure is going to be a fraction, and therefore unitless. So that gives us, when we do that calculation, for the oxygen, we get 0.192. Another way to look at this is, since we're reporting in a pressure, that's 0.192 atmospheres, because we're at 1 atmosphere because of standard temperature and pressure. So this is 0.19 atmospheres of pressure. So we can look at it that way. That gives us an answer in a pressure unit. Okay, so then in the other case, so that's our oxygen. So I'll rewrite this as just ATMs of oxygen. This other one here, we got 15.93 divided by that 44.6. That gives us 0.36, or 0.357 really, atmospheres of nitrogen. Okay, so you didn't even need to solve for the molecular weights or anything like that. Does this make sense? All right. So the last problem, kind of similar. Here, calculate the volume occupied by 5.2 grams of carbon dioxide at 152 kilopascals and 315 Kelvin. So again, we're going to use the ideal gas law. We want to know the volume. We're given a mass. We're given a specific pressure and temperature. So we're not at standard temperature pressure. We're just going to be filling in the numbers as needed. So the first thing we need to do is know the number of moles that we have given that 5.2 kilograms. So I'm going to say, I'll go ahead and convert that 5.2 kilograms into grams of CO2. We know the molecular weight of CO2. If you calculate that, that's 44 grams per mole. Oxygen is, O2 is 32. Add 12 to that for the carbon, get 44. So we can say, if we take that 5,200 grams of CO2, divide that by 44 grams per mole, that'll give us the number of moles we have in the system, which would be 118.18 moles of CO2. Okay, so that gives us N. What we're looking for is the volume. So if we rearrange this, it's going to be nRT divided by the pressure. And you could keep everything in kilopascals if you wanted to and use the R that's associated with kilopascals. I decided I wanted to just use that same R value, same units for it. So I'm going to go ahead and convert from kilopascals into atmospheres. So we have the N, we have the R that we're going to use. We used the same one last time. Temperature, we have it in Kelvin, so that's going to be 315 Kelvin. And then the pressure down here, what I'm going to say is we'll take these 152 kPa and essentially multiply it by 1 ATM divided by this is our conversion here, 101.325 kPa. You have this conversion on your formula sheet, so I did post the formula sheet that I will put in the back of your exam. So you'll have that conversion sheet, you'll have the R, a couple different values for R on your exam. So definitely familiarize yourselves with that if you have not. That's on Moodle. So when we put all those together, we just listed the R a minute ago and we just solved for the N, so I'm not going to bother rewriting all that. Then our volume becomes 2,036 liters. Okay. Any questions or issues?
Sorry, what you said the value of R was again?
R, we used that a moment ago. R is...
Is it 0.08 to 1 or 800 to 1? That was the math.
0.820,
Okay.
yeah,
Okay, thank you.
821.
Appreciate it.
56. And that that'll depend on which units you're using here.
Yeah. Okay. Thanks.
Okay. All right. So hopefully that was relatively straightforward homework, but good practice familiarizing yourselves with dealing with concentrations, mass balances, basics, and all that sort of stuff. Homework 2 got into a bit more derivations of mass balances themselves and a little bit of Excel work. So this the first problem gives us some data, 3 data points, and says this was a 5% solution of phenol. The results of his experiments are tabulated below, and assuming this was performed in an ideal batch reactor, determine the decay constant for the disinfection of anthrax. Include the appropriate units for your answer. Now, if we were to be taking a closer look at disinfectants in general, we would include something to distinguish the concentration of the disinfectant itself. In this case, it's just generally what's the rate constant for this disinfection in this case. So we're not, we'll learn about that in water and wastewater treatment, if not some other class, but essentially this 5%, it's context about the problem, but we're not going to use that in the problem, although it's simple and maybe we'll touch on that later, but right now we're just looking at the problem, and for this one, it was a pretty simple one to do in Excel, so I'm just going to bring over my Excel sheet, take a look. So we basically just put the numbers in, got a time, got a number, and then in order to transform it from this nonlinear thing that's going to be kind of like can't draw a straight line through the points as they were. If you remember, we need to linearize them, so to take the natural log of n over n naught, so that's going to be feeding into our batch kinetics. So essentially what we're looking at is the n over n naught is equal to the e to the minus kt, right? And if we take the natural log of that, it just becomes minus kt. So what we're looking for is a value of k, and if we plot that as n over n naught versus time, then the slope of this line is k. All right, so the rise over run here, because that's, we could divide both sides by t and literally say, okay, the y divided by the x is k, it's minus k. So that gives us a way to find our k there, and when we did that, we plotted it and put the y, put an intercept here, and the y is 0.0154. So the k here technically should take out the negative, right? It's a should be negative that. So 0.0154, and this is in per minutes because the time that the x-axis here was in per minutes. I spent a few minutes to make the graph pretty. I'll show you how to do this in Excel at a later time, but you can add a second axis to grid it on each side with nice little tick labels and all that. So I'll demonstrate that in person, hopefully with a bigger screen or maybe some more better way to view it. Anyway, hopefully you did more. You at least labeled the axes and stuff like that. That was part of what I want to see is you doing that. I guess this one didn't ask you to make a graph. One of the next ones does. But at any rate, that's how we did it. That's would be the answer. So that was 0.0154, I think, per minute. Technically, for this one, you could easily use a graphing calculator instead. That would work. And any questions or issues with that?
I'm getting like a different number. Is the ln, the natural log of n over n not equals negative kc? I'm getting like 0.018. So,
When you say you're getting a different number, are you using a regression?
what?
Are you using a regression?
Is it bad? I don't know what that means.
So on Excel, what you should be doing is adding a linear regression to find the line of best fit.
Oh no, I didn't even do that. I used the ln and not. I just calculated it on paper, and I'm getting like 0.18.
Okay, so you calculated on paper, but what did you calculate? The rise over the run?
Yeah.
I mean, technically.
Oh, never mind. I'm getting the right answer now. I don't know what's going on.
Okay.
I did the wrong thing. Okay.
All right. Good.
I was gonna ask on the test, like, if there were questions similar to that, is it just be looking for the k value, you don't have to draw a graph, or will we have to draw a graph on the test?
Okay, for an exam, I probably won't ask you to do this, to do a regression system. I might ask you to draw a graph or something, or what something would look like. Sorry, what exactly was your question again?
It was more if you're gonna be mainly looking for just the k value, or if we'll have to draw a graph.
Okay, yeah, so will you be manually looking for k value? No, because I'm not going to ask you to do a regression. I assume you know how to do that, or it could take a few minutes, with the homework or whatever. But I'm not going to test you on your ability to use a calculator that way. I think you should be able to, but I'm not going to bother with that. Rather, like you said, I might ask you to draw something or show a difference between the natural log of something versus just plotting it out as y instead of, or as a n instead of natural log of n over n naught, something like that. So be ready to draw some graphs, maybe. I haven't designed the test yet, but yeah, we won't solve for the k there. Okay. So problem 2, we have a water tower containing 4,000 cubic meters of water. This is taken out of service to install a chlorine monitor. The concentration of chlorine in the water tower was 2 milligrams per liter when the tower was taken out of service. We assume that the tank acts as a batch reactor while out of service. So when it's out of service, the water is not flowing. We've got some tank here on a tower. And so normally we've got water flowing in and water flowing back out, distributing. But during the out of service period, it's just a batch, and we're just going to pretend it's well mixed. We've got some volume, you've got a concentration, and we're going to have some rate constant where chlorine decays over time because it's reactive. So just drew a system, encourage you to do the same. Now we have some information here, and now that it's acting like a batch reactor, we know that it's going to be, we can just follow the mass balance for a batch system. And then the problem is asking us if the chlorine decays by this rate constant, what is the chlorine concentration when the tank is put back in service 8 hours later? So essentially we're just solving a mass balance for a batch system, which is relatively simple, given a time of 8 hours. Okay? So in a batch system, we know that V dc dt is equal to, in this case, we take a look at our rate constant. That's a per time unit, so that means it's a first order rate constant. So this will be negative k times c to the 1 power for the first order times v. You know the drill. V's cancel. We can integrate this. We'll end up with some form of natural log of c over c naught equals minus kt. Now in this case, what we want to know is the concentration after 8 hours. So we'll take this a step further, say c equals c naught times e to the minus kt. And really we have all the parameters there. We just need to make sure that our units are in together correctly, and then we solve for the concentration at 8 hours. So c equals our initial 2.0 milligrams per liter times e to the minus k, which is in per days. We'll need that in hours, so let's just say 24 hours. Or I'm sorry, I'll just write it up. So we'll have the 1.0 per day, day to the minus 1, and then we have the time in 8 hours. We'll go ahead and convert that to days. We'll take that 8 hours times 1 day per 24 hours, so a third of a day. Then it should be relatively simple to calculate there, given that. When we do that, we'll get 1.4 milligrams per liter. Okay, so then part B asks what mass of chlorine in kilograms must be added to the tank to raise the chlorine level back to 2.0 milligrams per liter. So here's where we will need that volume. So we have, we need 2.0 milligrams per liter, and that's got to be in our volume. So if we take that concentration times the volume, that's going to be our total mass, right? So we'll go ahead and write this in as 4,000 cubic meters. This is going to give us a mass once we convert from liters to cubic meters. That's in milligrams, and we need an answer in kilograms, so we need to convert that too. But this is the mass that you'd have to add going from 0 to 2, right? So what I'm going to do, instead of just write it straight up like this, what I'll do is we'll say 2 minus what we already have, which was 1.4 milligrams per liter. That times our 4,000 cubic meters. And of course, we need to convert. So let's say, let's go ahead and say times 1,000 liters per cubic meter. That gets rid of this cubic meters. That'll get, and then those liters will cancel. And let's go ahead and convert from milligrams to kilograms. So we need kilograms on top, so 1 kilogram per 10 to the 6 milligrams. Because you multiply by 1,000 to get to grams, you multiply by another 1,000 to get to kilograms. Okay, so with all of that, did I do something wrong? No, okay. So with all of that, we see that the 1,000 divided by 1,000,000 here, that's like dividing by 1,000 instead. we could actually simplify this very easily and say this is like 0.6 milligrams per liter. Well, let me just leave out the units for a second. That 0.6 here for the difference times 4, because that's going to be, we'll take that 1,000 out of that. Those thousands will cancel with a million here. So this is going to be kind of our answer once we do it all out. So I'll just say mass then is equal to, and we'll just take a look. Done it right. 2.3 kilograms. Which kind of makes sense. That's going to be our about 4, that 0.6 times 4, right? All right, so that was kind of a straightforward task to say, okay, well, we're missing some amount. How much do we need to add from this point? Okay, problem 3, we have a sewage lagoon. It has a surface area of 10 hectares, and I had to look that up, but that's I think each hectare is 100,000 square meters or 10,000 square meters. 10,000 square meters, so with the 10, it becomes 100,000 square meters. So, you have to look this up either in the appendix or online. Of course, on an exam, I'll either give it to you or expect you to, it's simple enough for you to know, something like that. Got a question?
On the exam, are we going to have to know that when it's a first order decay reaction, it's going to equal to negative KT, or is that going to be on the formula sheet?
The formula sheet is posted. So the question is, are you going to have to know for a first order reaction?
On the one we just
Yeah, so on the one we just used, a first order reaction that, if we could write something like this, dc dt is equal to minus kc. What you're going to need to remember really is just that there's an n value here, and that n equals the reaction order, right? So do commit that to memory. It's not on the formula sheet. So if 0 order, that becomes minus k times 1, right? Because anything to the 0 power is 1. So that goes away. If first order, that becomes minus kc to the 1 power. For second, kc squared. So you should remember that. I do expect you to know that. So good study point if you have not already committed that to memory. Okay, and we're going to see another reaction that's also going to be a first order decay here. So in this problem, we have this very large area receiving, and it's a lagoon, so it's a very large system, receiving 8,640 cubic meters of sewage per day, and that contains 100 milligrams of some biodegradable contaminant. At steady state, the effluent from the lagoon must not exceed 20 milligrams per liter of the contaminant. So let's go ahead and draw a lagoon. And we have some wastewater entering it. We have some volume. It says, assume it's well mixed. Has some discharge out the other end. So we have some flow rate coming in, some C inside, some K for a reaction, some initial concentration of that biodegradable contaminant coming in, and here we go. Okay, so I just drew it up based on that, and the question says, what biodegradation rate, reaction rate constant, or coefficient, per day value, must be achieved for a first order reaction? Okay, so K here is the question. We're actually given pretty much everything else. So C naught here, that is, the entering is 100 milligrams per liter. What's exiting here, and what the same thing that's in here, it can't be more than 20 milligrams per liter, so we'll just set that at 20. So that should be our kind of our starting point there. We were given the flow rate. Q was 8,640 cubic meters per day. And so now we just need to solve for first the volume and then K. And for K, we'll need a mass balance for volume. We have this 10 hectares as a surface area times the depth. So this is going to be depth times the surface area. Depth was 1 meter, so we can just say that whatever that area was, it's that many cubic meters. So let me pull this aside so I can write it out for you. A little more clarity, I hope. Okay, so when we did that, and taking a look at the conversion for hectares, it turns out that the volume is essentially 10 to the 5th cubic meters. Because this was 1 meter times 10 to the 5th square meters gives us 10 to the 5th cubic meters. Okay, so with that, we are now ready to solve our mass balance and solve for K with that. We know this is at steady state, so we can start off by saying 0 equals what's coming in minus what's going out, plus that reaction term, which is a decay reaction, so that's going to be in that volume times K times C. So with that, this is a fairly standard, or CSTR reaction. And in this case, what we want to know is K. So we're going to solve for K. I'll go ahead and divide everything by Q. That gives us a theta here times K and C. So we'll go ahead and put the theta Kc on the left equals C naught minus C. And then essentially we just divide everything by theta C. K equals C naught minus C divided by theta times C. Second guessing myself for a moment here because I think I wrote something else in my solutions earlier today. I'm confident that this should be the right approach. So let me know if you see something missing or that doesn't work here. But let's go ahead and let's get theta here. That's V over Q. Make sure that I'm not going crazy over here. So V over Q, that's going to be our volume, which was 10 to the 5th cubic meters, divided by the Q, which was 8,640 cubic meters per day. That gives us an answer in days, which was 11.57 days. That's our hydraulic retention time. So water on average stays in this pond for almost 12 days. Seems reasonable enough for a large pond, large flow rate here. That should also give us, when we solve, that should give us a rate constant in days. Okay, so I think what happened was I solved it here just from the first principles. In my Excel sheet, I decided to start from C equals C naught over 1 plus theta K. So this is something you might end up doing if you memorize that the derivation for a first order CSTR at steady state. This is what it looks like. So if you started from here and solved for K, then you might end up with an expression where it looks like K equals C naught over C minus 1 divided by theta. And I think that's the same expression. We just factored something out. So that's why I was stopping myself from getting confused. Algebraically, if you do it correctly, either way works, right? It's just algebra. So I'm just going to assume that for a moment that I did that correctly. And our K should be 0.35 per day. And just to convince myself that this is correct, and I'm not lying to you, we're going to double check that here. Actually, you know, we've got 10 minutes, so I'll double check that on my own time. I think it's correct. I want to go through problem 4 with you. So it says, use an Excel sheet or equivalent to determine the effluent concentration of the process producing, if the process producing sludge shuts down so that the Cn is equal to 0, and then calculate and plot points at 1-day intervals for 10 days. Use the chart function, and then generate a graph printout for this assignment. So before we get to Excel, what happens is we're no longer at steady state, right? So we have a decreasing amount of this contaminant in the pond because we were at steady state and then we cut off the influent, and so now it's draining away this stuff, right? So we have the accumulation term equals 0 coming in, minus what's going out. We still have a QC here. And again, we still have minus V, K, and C. Well, it turns out this is actually rather simple, which is nice, because we can integrate. Let's go ahead and divide everything by V real quick. So we have dc dt equals negative Q over V minus KC. Sorry, that's times C here. We can take a minus C out of that whole term. So dc dt equals minus the concentration times Q over V. Since I took the minus out, I factored out the minus, then it should leave us with a plus K here. We can move the C over to the other side and the dt to the other side, so that becomes dc over C, something we've seen before, equals minus Q over V plus K dt. And that's something we can integrate because we know that the stuff here, the Q and the V are constant, the K is a constant. So this just becomes essentially a batch system where we have almost the same as a batch, except there's something to do with the Q and the V there. So when we integrate, we get the natural log of C over C naught here equals minus, instead of minus KT, we get minus this stuff times T. So we have minus Q over V plus K times T. Otherwise, it's going to play out very much like a batch system. So it's like kind of almost the same. We could rewrite that as C over C naught, or you know what, we could just write that as C because we'll solve for C, right? We'll say C equals C naught times E to, instead of minus KT here, we'll say minus the Q over V plus K, all that times T, okay? So this was a non-steady state system that had a fairly simple solution, just recognizing that it's the same derivation once you factor out that C, and these guys are constant. So coming back over to Excel, then it was really just a matter of putting in that formula, the C equals C naught, which is our 20, times E to the minus V over Q plus K, all that times the time. And it told us to calculate at time intervals of 1 day. So the first time point would be 1 day, 2 days, so on. And so we just do a series of time intervals there and calculate the concentration for it at that given time interval. So once you set it up, you should be able to fill it down like so. And then when you graph that, I went ahead and copied the formatting that I had done on the previous one. Again, I'll show you that later. But you should have some form where if you track C over time, it's decreasing kind of that exponential look. Or, yeah. So the exponential decay there. So you could, of course, plot that with a natural log, and you'd get a linear plot or something that's probably linear. But it just asked for C over time. So that's kind of what I was expecting. Any questions or issues with that? Does that make sense? All right, and it turned out that the next problem actually was kind of similar. So I'll just say this, that this also happened to be the same sort of system where we had some concentration, we had a flow rate leaving, the venting system, and then it was decaying the same mass balance applied because it was a non-steady state system acting in the CSTR. So it's really the same process, just with a different context. I'll solve that. I'll put these notes online for you soon, today, and that'll be there. I'd like to give you a few minutes if you had any other questions about the exam or concerns. Again, I will keep it relatively shorter than what I would normally do, because I know a lot of you will be brain dead, and I have sympathy for you. I'm sorry about that. And if yeah.
If we memorize the equations for like first and second order, we have to show the calculus to derive it.
Okay, so the question is, if you memorize the equations for the first order or zero order, stuff like that, do you have to show the calculus of derivations? No, just be honest with yourself whether or not you're comfortable getting there for a first order growth equation, or something like that. So I've a lot of what we do is a decay reaction, but the same principles apply for growth. So you should be able to do that sort of stuff. So just be ready for a system that's not precisely what we've done, but using the same tools. So I don't mind if you memorize, just make sure that you've learned it and it's just handy to memorize, okay? Yeah.
So we didn't really have to worry about the second order.
Yeah.
Take notes so we won't be able to test it.
Regarding second order reactions, I'm not going to have you solve any solutions for second order, but I do expect you to be able to derive the units for a second order rate constant, or recognize that a rate constant with some units, which order that is, including second order. So be familiar with deriving the units for a given rate constant. And that comes right back to what I mentioned earlier. The units here for this, they have to match that dc dt. So depending on that reaction order, the units of K change. So just be familiar with that. I might ask you something second order in that regard, but I'm not going to have you do an integration on a second order thing. Yeah. Any other questions? Yeah.
So you're going to make it shorter, so like how long is it going to be? Like how many questions?
So my target will be that most people should be able to finish it between 40 minutes and an hour when you have an hour and 20. And that's probably, from my experience, and again, I haven't taught this class before, but I would guess that would be about 3 questions that each have a couple parts, something like that. Fortunately, the first section here, a lot of it was just kind of review over units, basics of, not particularly complex things. I mean, the reactions and stuff gets more complicated, but part of this whole first unit was just, hey, do some unit conversions, right? So hopefully that's not too taxing. Any other questions or concerns, issues? All right, so I will email you after the exam regarding when I'm doing the kind of post-exam, like here's the solutions, walk through them, that's our makeup day, and I'll email you also about the details for next week in case you forget. All right, so we'll see you on Thursday.